Hey guys, how's it going? Hope everybody's doing all right today. Hopefully you saw the second video I put up on Tuesday. I finished out that fifth example, redid it basically from start, and it worked out a lot better using y as positive. So we got an exam coming up Tuesday. It's going to be chapters 1, 2, and 3, but pretty much just 2 and 3. Pretty much focus on chapter 2. Obviously, just like we're only going to do one problem from chapter 3, so tank problems. So just focus on that stuff. Don't worry about too much from chapter 1, maybe just a little bit. It's really just knowing, like how do you know you have a solution to a differential equation? Well, you differentiate it and substitute it in. So let's see. Today we're going to start chapter 4, and that's linear differential equations basic theory. So it's going to be like higher order differential equations and the theory of higher order equations, but they're going to be linear. So this is all about higher order linear equations. So that's pretty much our focus today. We're going to try to get into the next section as well. We're going to try to get into reduction of order. It's pretty short as far as the section goes, so I'm hoping we can get through chapter 4, section 1, and then get into reduction of order as well. But we shouldn't have any trouble doing that, I don't think. So the first thing we're going to talk about here in this section is it's basically 4.1. We're going to talk about first initial value problems, and we've mentioned this a little bit in chapter 2, but this is more of the general theory. So initial value problems for a general nth order differential equation would be of the form a sub n of x nth derivative of y plus a sub n minus 1 of x times the n minus first derivative of y plus a1 of x y prime plus a0 of x y equals g of x. And we have initial conditions y of x0 equals y0. Also y prime of x0 equals y1, all the way out to n minus first derivative evaluated at x0 equals y n minus 1. So this is what we call the general linear initial value problem. So this is the most general way you could think of this problem, initial value problem, IVP. You might see that phrasing IVP, or initial value problem. So it's a general initial value problem. Now we have an nth order equation. It's a linear, so this is an nth order linear initial value problem. Initial value because all of these places where in our initial conditions are the same. So x0, 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 it's all the same. So we call it an initial value problem because all the conditions, y, y prime, n minus first derivative, they're all being evaluated at the same point. So when you have those as your conditions, we call it an initial value problem. So conditions for a unique solution. I'm not going to focus on this a lot in the class, but just to be thorough, conditions for a unique solution. Well, we have to have these two conditions satisfied. The first one is the coefficients ai of x and the right-hand side g of x need to be continuous on some interval I. Capital I, we'll call it. So that's the first thing. We need these functions, the coefficients, and then the right-hand side of the differential equation. We need all these functions to be continuous on some interval, capital I. And the second thing is we need an of x to not be equal to 0 for all x in the interval I. So the leading coefficient basically needs to be non-zero for all x in I. Now, if our initial position, or our initial x0, now if x0 is in capital I, then y of x, the solution, is unique. So that's how we know we have a unique solution. Basically, we need these two conditions to be satisfied. Then we can say that we have a unique solution if our initial x0 is in the interval I, where our functions are continuous. So that's the general idea of a boundary value problem. I'm not really going to ask you for uniqueness necessarily in this class, but just to be thorough, that is the conditions that we need for, or those are the conditions we need for a unique solution. Now, there is something else called a boundary value problem. So a boundary value problem might call that BVP, boundary value problem. So this is basically going to be where we could have like the conditions being evaluated at different x values, not all at the same x0, but maybe at different x values. So for example, might have a second order boundary value problem, and it would look something like a2 y double prime plus a1 y prime plus a0 y equals g of x. And we might have the conditions y of a equals y0 and y of b equals y1. That would be a second order boundary value problem, because I have basically just y being evaluated at two different x values, so a and b. So that's a boundary value problem. We could have other boundary conditions. So these two conditions here, we call those boundary conditions. Boundary conditions. So we could have other boundary conditions. So other boundary conditions might be maybe something like y prime of a equals y0 and y prime of b equals y1. So maybe that would be our boundary condition. It might be like a mix and match kind of thing. It might be like y of a equals y0 and y prime of b equals y1. So like you mix the first derivative at a, or sorry, you mix the function value at a with its first derivative at b, and it's a boundary value problem at that point, because you have different x values going into your conditions. You get the idea. It could be something even more general, maybe could be like more generally, it could be something like alpha 1 y of a plus beta 1 y prime of a equals, call it gamma 1. So that might be our first condition. And then alpha 2 y of maybe a plus beta 2y prime of b equals gamma 2. And that could be, a different set of boundary conditions. The first equation is the first condition, the second equation is the second condition. So might have these two boundary conditions. So it's just a lot of stuff that you could do with your boundary value problems. They're much more involved usually as far as the conditions go for boundary value problems. But in general, you cannot guarantee uniqueness for boundary value problems. So uniqueness is harder to find in boundary value problems. Let me just say, for example, if we have a differential equation y double prime plus 16y equals 0, somehow magically, we'll find out later, the solution y is equal to c1 cosine 4x plus c2 sine 4x. And depending on your conditions, those constants, you might have one solution. Let's just say you have like y of pi over 8 equals 0. Somehow that tells us we have one solution. Only one set of coefficients, c1 and c2. So let's say we have y of these two boundary conditions, y of a equals 0 and y of pi over 8 equals 0, then you have one solution. Let's say the second one, you have y of a, just some number equals 0, and y of pi over 2 equals 0. Then you have infinitely many solutions. And then number 3, if you have y of a equals 0 and y of pi over 2 equals 1, that would give you no solution. So depending on your conditions, you might get many solutions, no solution, or one solution. Let me just say many solutions here instead of infinitely many. Just say many solutions. So that's our boundary value problem. Now it's not super common we're going to deal with boundary value problems, but we might throw some in every now and then. Most of the time we're going to have initial value problems, i.e. all the conditions are at x0, which means you have to only consider y prime, all the way up to the n minus first derivative of y evaluated at that one x point. So that's the start of our general theory. So the next thing we want to cover is homogeneous versus non-homogeneous equations. So our differential equation was an times the nth derivative plus an minus 1 times the n minus first derivative plus a1 y prime plus a0 y equals, and depending on what g of x is, we said it was equal to g of x. Now if g of x is equal to 0, we call it a homogeneous equation. So it's a homogeneous linear differential equation. If g of x is not 0, call it a non-homogeneous equation. still linear differential equation, but it's just non-homogeneous. We're going to have a whole section devoted to homogeneous equations, and then we're going to have 2 sections devoted to non-homogeneous equations, because there's different methods for solving the equations that are non-homogeneous. There's like an easier method that only works in special cases, and then there's a general method that works in all cases, but it's a little more complicated, so you don't necessarily want to use it all the time. But, well, I mean, you could use it all the time, but just more work. So, next thing we want to cover is something called differential operators. So really the terminology here is what we wanted to focus on. Now, differential operators our notation really is just dy dx could be written as differential operator acting on y. So capital D just means take the derivative of y with respect to its independent variable. So then the second derivative, d squared y dx squared, we could write as capital D squared of y. And then we might have a linear combination of these, and we might call the differential equation, we might say L is equal to an of x dn plus an minus 1 of x dn minus 1 plus dot 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 a1 of x d plus a0 of x. Then Ly would be equal to g of x. This is just another way to write a linear differential equation. Is just using this differential operator. Basically, this L takes y as an input and then sticks y into each differential operator. Here, all that you would do for a0 acting on y is just multiply. So L acts on y by plugging y into each differential operator. And for a0 of x, we just multiply a0 of x by y. No derivative is taken for the very last term. So L of y be equal to an of x and then the nth derivative of y plus dot 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 a1 of x d of y, it's the first derivative, plus a0 of x times y. So that would be L acting on the function y. That's pretty good. Good stuff. The linear operator L, so properties of L. Number one is that L of alpha y is equal to alpha times L of y for any constant alpha. So you can pull constants out of the differential operator. And we know that's true from calculus 1. Like derivative of a constant times a function is just constant times derivative of the function. So that's basically the same thing. except now we just have a bunch of derivatives being multiplied or added together, I mean. The second property of a differential operator L is that L of y plus, or y1 plus y2, so say you have two functions, y1 plus y2, that's equal to L of y1 plus L of y2. So these are called the linearity properties. Linearity properties of L. So you can pull constants out and you can break up the operator over the individual functions. Just like you can do a regular derivative, you know, like d by dx. So basically just recall d by dx of f plus g is f prime of x plus g prime of x. It's kind of the same thing, just we have a more general thing we call a differential operator. All right, so that's differential operators. Good stuff. Try to slow down a little bit. I know I'm going pretty fast. Take a breather, answer questions, see what's going on. Anybody heard any good jokes lately? Heard one today on the radio. The joke went, did you hear about the guy who had his left side cut off? He was all right. I'll be here all week. All right, sorry. I will never do that again, I promise. Oh, good. You finished a game. I assume that's a game, because I have no idea what it is. Half-Life ALYX, or Alex. Half-Life Alex. That's awesome. You suck at games, and yet you finished a game. That's awesome. Tough crowd. Yeah. You can say that again. I literally expect you to type that again. Good stuff, good stuff. All right, I'm sorry. I'll stop. So let's look at the superposition principle. So the superposition principle. Superposition principle for homogeneous equations. We'll say for homogeneous equations. So this says if y1 of x, y2 of x, all the way out to yn of x are solutions of L of y equals 0, then y equal to c1 y1 plus c2 y2 plus dot 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 cn yn is also a solution to the differential equation. So let's call this YH for homogeneous. So that means L of YH equals 0, because L of YH would be equal to C1 L of Y1 plus dot 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 Cn L of Yn, using our linearity properties. And now we know all of these are 0. 0 plus dot 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 plus 0 equals 0. So we have a general, what we call a general homogeneous solution if we have a bunch of little solutions. And where do we get those little solutions? We'll talk about that soon enough. But that's called the superposition principle, in that you can add two solutions together and get a new solution. And you can multiply those solutions by a constant and then add them together, and it's another solution as well. So yeah, that's the idea of the superposition principle. We're going to make use of that quite a bit throughout the course, so don't forget it. It's pretty important. The next thing is the linear independence and linear dependence. So linear independence of solutions. Okay, so first thing I want to do is define the Wronskian. It's a definition. The Wronskian of functions, we'll just do a simple set of three functions, y1, y2, y3, is w of y1, y2, y3, and it's just a determinant, 3 by 3 determinant. y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, y3 double prime. If you just had two functions, if we have just y1 and y2, then the Wronskian of those two functions, y1, y2, be equal to y1, y2, y1 prime, y2 prime. So that would be the Wronskian. So there's a theorem. Let's see, I guess I better define linear independence before I check for it. So definition: a set of functions, call it y1, y2, yn, is called linearly independent. Called linearly independent if c1 y1 plus c2 y2 plus dot 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 cn yn equals 0 implies c1 equals 0, c2 equals 0, and cn are all 0. That's what we mean by linear independence. The only way to make this linear combination, this equation, basically true, is to have the coefficients all equal 0. Then the functions are called linearly independent. If there were one coefficient that were not 0, I could basically solve for that coefficient in terms of everything else. I could solve for one function in terms of all the other functions. And then one function would be a linear combination of the others. We'd call that linearly dependent. So that's what it means to be linearly independent, is that the only way that this equation with the red star can be satisfied is if we have all the coefficients equal to 0. Now, that's really hard to check. So what we can do is check the Wronskian instead. So theorem, if the Wronskian is 0 for a set of functions, then the set is linearly independent. Otherwise, it is dependent. Sorry, non-zero. If the Wronskian is non-zero for a set of functions, then the set is linearly independent. Otherwise, if the Wronskian is 0, then the set of functions is dependent, linearly dependent. It just means one of the functions can be written as a combination of the other functions if you're dependent. If you are independent, there is no way to write any of the functions as a combination of any of the other functions. Yeah, Wronskian. W-R-O-N-S-K-I-A-N. Wronskian. I think that's a guy's name, just guessing. I'm pretty sure it is. Wronskian. So if the Wronskian is non-zero at any point in some interval, then the set is linearly independent. If it's equal to 0 for all points in some interval, then you're linearly dependent on that interval. So, example, let's show are the functions linearly independent? So, are the functions linearly independent? So the first set of functions, we're going to say y1 is going to be e to the t. y2 is going to equal e to the negative t. And the second one, I have the set S of functions is going to be t squared and 3t squared. The third one, the set is going to be the set of functions 1 comma t comma 3 minus 2t. And then the last one, the set is going to be the set of sine x cosine x, and 1. So just write it all the same. Means the same thing. y1 equals e to the t, y2 equals e to the negative t. Well, that's just the set of functions e to the t, e to the negative t. Now, how do we check to see if they're independent? Well, we're not going to use the definition. We're going to use the Wronskian. So solution, part A, calculate the Wronskian of y1 comma y2. So that's going to be y1, y2, y1 prime, y2 prime, since I only have two functions. That's going to be the determinant, e to the t, e to the negative t, and then take the derivative. That's just e to the t here, and then negative e to the negative t here. Now, that determinant is going to be negative 1 minus 1, which is negative 2, which is not 0. Therefore, set is linearly independent. So if the Wronskian is non-zero, just go back up to our theorem. If the Wronskian is non-zero, it's linearly independent. If the Wronskian is 0, it's linearly dependent. So, good first example. Let's continue. Part B. We have, again, two functions. So we have Wronskian of y1 comma y2. It's going to be y1, y2, y1 prime, y2 prime. It's going to be determinant t squared, 3t squared, and then derivative is 2t and 6t. Now, that's going to be 6t cubed minus 6t cubed, which is 0. Therefore, the set is linearly dependent. So just notice, I can rewrite 3t squared as 3 times t squared. So they are not independent. I can write one of the functions as a combination of the other function in terms of the other function. So they're not fundamentally different functions. They're like the same function. They're just like a constant multiple away from each other, or a combination of the other. So let's look at part C. Here we have three functions. Wronskian of y1, y2, y3 is a 3 by 3 determinant. y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, y3 double prime. So that's going to be, let's see, 1t, 3 minus 2t, 0, 1, negative 2, 0, 0, 0. And if you have any experience with determinants, you'll know that there's a couple of things to do. If you have a row of all zeros, the determinant is automatically 0. If you have a diagonal matrix, or sorry, an upper triangular matrix, you can just multiply the diagonal elements, you get 0. So either way, you're going to get 0 on this determinant. So this means the set is linearly dependent. So linearly dependent. Well, think about this. Y3 is actually just 3 times y1 plus -2 times y2. So they're linearly dependent. I can write y3 in terms of y1 and y2. So that means they are linearly dependent. Because I can write one of the functions in terms of the other function. They're not fundamentally all different from each other. One of them is a combination of the other two. And the last one we have sine x, cosine x, and 1. So again, we have 3 functions. We have to do a 3 by 3 determinant. So sine x, cosine x, and 1. Part D, take the Wronskian of 3 functions, y1, y2, y3. And that's going to be sine x, cosine x, 1. Now take the derivatives. We're going to get cosine x, negative sine x, 0, and negative sine x, negative cosine x, and 0. Now this 3 by 3 determinant, you can expand along any row or column. Normally we expand along the top row. So I'll do that, sine x times 2 by 2 subdeterminant, 0 minus 0, minus cosine x times the subdeterminant, 0 minus 0, plus 1 times the subdeterminant, negative cosine squared x, minus sine squared x. So I'm just doing the 3 by 3 expansion, and that equals 1 times negative 1, which is negative 1, which is not 0. Therefore, the set is linearly independent. So that's what we mean by checking for linear independence, is really just to check the Wronskian. So sine, cosine, and 1 are fundamentally different functions. You can't write 1 in terms of the other two as a linear combination. Maybe a nonlinear combination, because we know sine is equal to plus or minus the square root of 1 minus cosine squared, but that's very nonlinear. So a linear combination means just multiply by a constant and then add the functions together. So that's linear independence. And that's really the biggest thing to take away from the section, honestly. I mean, other than the terminology and just knowing, is it homogeneous, is it non-homogeneous, knowing the superposition principle, what we mean by initial value problem, boundary value problem. The biggest thing to take away from that, or from this section really, is just the way to check for linear independence. That's really the only computational aspect of this section. So that's what the homework problems are really going to focus on, is just checking for linear independence, linear dependence. So any questions? Take a second, take a breather again. Cool. So yeah, not a whole lot as far as like actually doing any kind of computation in this section, just linear independence. I think we're almost done. We're going to focus now on the general solutions of these differential equations. So the general solutions of our differential equation. So the general solution of something like an nth derivative of y plus ... a1 y prime plus a0 y equals 0. There are n linearly independent solutions to this equation, and that set is y1, y2, ... yn. So there are n linearly independent solutions to this nth order linear equation. So then the general solution is y equals c1 y1 plus c2 y2 plus ... cn yn, where c1 c2 ... cn are just constants. So that's your general solution to the homogeneous linear differential equation, nth order linear differential equation. We'll talk about how to find these solutions, y1, y2, yn, as we go through chapters, the next section 4.3 after today, so that'll be next week. But for now, just know that they will exist. For an nth order equation, there are always n linearly independent solutions. And they are, of course, they're linearly independent. So that's the general solution. Another example. I'm not going to tell you how to get these, but y double prime minus 9y equals 0. The independent solutions are y1 equals e to the 3x and y2 equals e to the negative 3x. So then the general solution is, we'll call it yh equals c1 e to the 3x plus c2 e to the negative 3x. And so that would be the general solution to the differential equation. How do you verify that this is actually, that y1 is a solution? So why is y1 a solution? How do you know? Well, you take y1 prime, that would be 3e to the 3x, y1 double prime, that would be 9e to the 3x, and sub into the differential equation. So that would be 9e to the 3x minus 9e to the 3x, and that equals 0. Check. So y1 is a solution of the differential equation. Right, this first thing here, that was y double prime, y1 double prime minus 9y1. So that's basically what we did. So that's a good way for you to check in general, is the function that I have actually a solution to the differential equation? Just take its derivatives and plug it in. It's the easiest thing to do, for sure. So that's the general solution of a differential equation. Now, what about a non-homogeneous solution or a non-homogeneous equation? So now consider a n of x nth derivative plus dot 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 a1 of x y prime plus a0 of x y equals g of x. So the first thing you always want to do when you solve a non-homogeneous equation, so this is non-homogeneous solutions, general solutions. The first thing you want to do is find the corresponding homogeneous solution. Y h of x equals c1 y1 plus dot 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 cn yn. That solves L of y equals 0 instead of L of y equals g of x. So first thing you always do is find the complementary, it's what we call the complementary solution or the homogeneous solution. So complementary or homogeneous solution. So that's always the first step. Then the second step is find a particular solution. We call it yp of x. Let me write that up here. Yp of x. Step 3, form the general solution. Y of x equals yh of x plus yp of x. So that's our general non-homogeneous solution. We'll talk about how to get yh and yp in the rest of the chapter, but just the general solution is always going to be of this form for a non-homogeneous equation. And then the last thing for non-homogeneous would be like a subpoint if g of x is equal to something like g1 of x plus dot 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 gk of x, then we have yp be equal to yp1 plus ypk of x. So our particular solution would be like a superposition of the individual particular solutions. So it's like a superposition of particular solutions. Superposition of particular solutions. If you have a g of x, that's already a superposition of functions g1, g2, all the way out to gk. So that pretty much finishes up the most boring section that we have to cover, honestly. So not the most exciting section for sure. So hopefully I hung in there, made it through. Let's take 5. Just take a break for a second, let everybody catch up. Just take a little bit. We'll be right back. Cool. So I think we're back. Any questions? It's been about 5 minutes, I think. Take a little time. Any questions at all? Feels like we're a little slim on the participants here, but I guess people can watch later, of course. But always a good time to get together, ask questions, see what's going on. I personally, I just can't do it. Like, if I get behind in something, it's really hard to catch up. Like, I can't like let myself mentally do that. So I try not to, if possible. I try to stay on top of it. Just stick with the normal time. But of course, that's just me, and I have, issues, obviously. So let's look at reduction of order. So let's flip over to a different section here to something called reduction of order. Yeah, the test, actually, it's just going to be, I think it's just going to be 7. I hate to like give away too much, but it's just going to be 7 questions. Shh. Don't tell Dr. Ming I told you everything. It's going to be 7 questions. No, just don't worry about 2.1. Just basically starting with separation of variables. I mean, there is like a question from just, understanding what does it mean to be a differential equation and all that stuff from chapter 1, but really starting with chapter 2. So yeah, so something like that, Jack. I'm not sure like how that's going to work. Like Dr. Ming, like he wants to do like 20 minutes of lecture after the exam, so basically like start at 9:30. What I was thinking about doing was just posting a video, like just a standalone video without you guys having to actually show up for the video, like a live stream or whatever. So might just do that instead of like whatever. I don't know, we'll see. I don't think I'm going to do a live lecture after the exam. So you're going to have an hour for the exam and then 10 minutes to upload or whatever. So then that puts us at like 9:10. And then, yeah, I don't know. We'll see. I'm not sure. I might just make my own video, upload it. We'll see. So yeah, it's a pretty stout exam. I mean, it's not easy. I mean, it's not hard, but it's definitely doable. Like everything in there is doable. It's open book, open notes, like we said. You can even use a calculator. I think one probably might even need a calculator. So yeah, just hang in there. It's not gonna be too bad. It's gonna be very similar to the problems we work. So yeah, the fact that we only have 7 problems really helps with the difficulty, and the fact that you can use your book, like to look up the formula. Like you don't have to just whatever. You can. You should basically know how to do every problem. Whether or not you get all the details right, that's the issue. Like there should be no blank problems. So that's what we're kind of like balancing out, is now that you pretty much are going to know how to do every problem because you have your book and your notes. It's just getting all the details right. So that's the difference of taking a test like this. No, you don't have to print it out. I'll give you details of how to like submit the exam and all that stuff, but you don't have to print it out. I just will want you to work each problem on its own sheet of paper and then scan those in order and put them in a PDF and upload it. So you'll have the PDF that I give you. It'll have the problems on it. They're all on one page. You'll see problem 1. Well, then you need to, on your scratch paper, have a paper that's devoted just to problem 1, and you write your solution. And then you have a sheet of paper that's devoted just to problem 2, and you write out your solution. And then you have a sheet of paper that's devoted just to problem 3. You write out your solution, etc. And so you do that for all 7 problems. And then you scan them in, create one PDF, upload it to Moodle, just like we did in our practice assignment. I just really need you to make sure that your pen is dark, or your pencil or whatever is dark enough to show up on the scanner, because we really need to be able to see your work if we're going to grade you appropriately. So really, really try to keep that in mind when you're working. Make sure it's visible. Try to make sure it's dark enough. Other questions? Yeah, so now the technical difficulty is really just everybody's on it like an even plane as far as starting out. You all know how to start the problems now because you have open book, open notes. Now it's just, can you do the detailed math to get the solution correct? So we basically budgeted about 9 minutes per problem, which some of them you definitely don't need 9 minutes. Like, you can do probably a couple of them in under 2 or 3 minutes. So that gives you a lot of time for some of the more technical problems. So yeah, it's gonna be start at 8 o'clock. Extra time, students, I'll probably start, well, since we might not do a live lecture afterwards, I might just extend the extra time students to 30 minutes after. So basically like 9:30, and then you can have till 9:40 to upload for the disability services. Yeah. Other questions? Cool. Now, reduction of order, it's pretty simple, at least what you have to do. The derivation is pretty complicated, but I'm not going to go through the derivation because it's basically the same thing we're going to do in a later section. So I'll just do the derivation in a later section, and it's very similar to that derivation. So I'm not going to do the derivation here for reduction of order. But reduction of order says given second order differential equation y double prime plus p of x y prime plus q of x y equals 0. So this is what we call standard form. So given a standard form of a second order linear differential equation, let y1 of x be a solution to the differential equation. So somehow you've already got one solution. Skip derivation. It's basically 4.2. Skip the derivation. See derivation 4.6 later for a similar approach as to what we do here to get this formula. So if you really want to come back to this after we do 4.6, feel free. So then a second linearly independent solution is given by y2 of x equals y1 of x times the integral 1 over y1 of x quantity squared e to the negative integral p of x dx and then dx. So that's your reduction of order formula. So basically it's just an integral. It's actually a couple of integrals. It's like an integral inside of an integral, and then you have to do the outer integral. It's really just a formula. Normally, of course, you have to remember that for the exams, but now we're going to do open book, open notes, so this should be a gimme problem. You just have to remember how to integrate. So we just look at one example here. So example, let's say if y double prime plus 4y prime plus 4y equals 0 and y1 equals e to the negative 2t, find a second linearly independent solution, y2 of x. So first thing we gotta do is identify p of x. P of x here is just 4. So y2 of x is going to equal e to the, let's see, I have t here, but I have x here. So let me change these here to t. y2 of t. Change this to t. Sorry about that. So we got everything in terms of t. So y2 is going to be negative, or e to the negative 2t times the integral of 1 over e to the negative 2t quantity squared, e to the negative integral of 4 dt and then dt. So that's going to be e to the negative 2t times the integral of e to the 4t. Right, doing a little algebra here. Square that by multiplying. That's e to the negative 4t in the bottom. That becomes e to the 4t when I move it up. Times e to the negative 4t dt. That's just going to be e to the negative 2t integral of 1 dt, which is going to be e to the negative 2t times t plus constant, which is equal to t e to the negative 2t plus a constant times e to the negative 2t. But I don't worry about that because that's just a constant times y1. And so we don't worry about that because we've already got constant times y1 in our general solution. So that will just go over to our general solution. So already in y sub h. So then y of t, yh of t will be equal to c1 e to the negative 2t plus c2 t e to the negative 2t. That's our general solution. So the y2, basically y2 would just be t e to the negative 2t. And then from there we can form our general solution. So that's good. It's a good example. We'll do one more here. And then we'll be done for the day. So example, if y1 equals x is a solution of x squared plus 1 y double prime plus or minus 2xy prime plus 2y equals 0, find y2 and the general solution. So first put it in standard form. First put in standard form. So that means divide by the leading coefficient. So y double prime minus 2x over x squared plus 1 y prime plus 2 over x squared plus 1 y equals 0. And now we've got p of x right here. So now y2 is going to be y1 integral 1 over y1 squared e to the negative integral p of x dx, which is going to be, see, the first solution is just x, so x integral 1 over x squared e to the negative integral negative 2x over x squared plus 1 dx. This is going to be x times the integral 1 over x squared e to the integral 2x over 1 plus x squared dx. Now to do this integral in the numerator, or in the exponent, I do a u equals x squared plus 1, du is 2x dx. So this is going to be x times the integral of 1 over x squared e to the natural log 1 plus x squared dx. And we know e to the natural log is just going to be, so 1 plus x squared dx. So this is going to be x integral 1 over x squared plus 1 dx, which is going to be integrate that, we get x times negative 1 over x plus x. And I don't have to worry about the plus c, we already know that from the previous example, so we're just going to drop the plus c. And then this is equal to negative 1 plus x squared, or x squared minus 1 equals y2. So that's y2, and then the general solution y sub h of x is going to equal c1x plus c2 times x squared minus 1. We don't use q of x, that's correct. We don't worry about that. Good question. Right now we don't use q of x for anything. Later we'll need q of x for something, but not for this section, not right now. Good question. So that kind of wraps up 4.2, reduction of order. So I think we'll just call it a day here. Kind of just try to digest. I know it's a lot of terminology, pretty boring stuff there at the beginning. Some computation here at the end. Hopefully it'll stick. Hopefully it'll make sense. The more you kind of just read over it, try some stuff, think about it. Just ask questions or whatever, of course. Start working on the homework. I guess just focus on the exam, then maybe Tuesday start working on a lot of the homework. But any final questions? If not, we'll just wrap it up and call it a day. All right, well, I'll just sweet, yeah. Adobe Scan's good. I heard that you can just use the Notes app in your iPhone, or if you want to use any of the scanners that you find online, just be able to create a PDF, a single PDF of all of your work. So that is going to be required for the exam. Sweet. Well, I think we'll call it a day, and you guys get some studying done. Hopefully, if you have some questions, you can hit me up on online office hours. I'm going to post a few more videos of just examples from Chapter 2 and Chapter 3 over the next couple of days. Hopefully going to get some exact stuff today, homogeneous equations today. I'm shooting for those examples today, just single videos of each example, and then try to work on some Bernoulli and other types of substitutions tomorrow, and then maybe some application problems by Saturday. So that's my goal, just to have a few more videos up, some more examples for you guys to look at, some more technical, hopefully technical stuff with initial conditions and all that stuff. So yeah, we'll call it a day here, and I'll see you guys on Tuesday. See ya.